Okay, guys, have to go back and get the camera. The key is posted upstairs on the 3rd floor. Test will be returned on Monday. You have the lab, Wednesday's lab. I forgot to give you this back in lab. The worksheet from the dial. After class, and in the class, I'll pass that back. The other half, we'll get it back this afternoon. Aromaticity. There is the medicinal chemistry info session today at 1 o'clock. It's offering 5 points extra credit towards the test on that. There will be a makeup. 10-page report on something if you can't make it. Hopefully you can make it today, right? Okay, MO diagram. We did an MO diagram of butadiene here. Do you have any questions about it? What do we end up with? When we put the electrons in, what do we see? I'm not going to redraw it. You should have it on your paper. We had 2 molecular orbitals that were completely filled. And then we had 2 molecular orbitals that had nothing in it. No electrons in it. The orbitals that were filled, were they bonding molecular orbitals or anti-bonding? Bonding. Importantly, this is the most important thing. When we put the electrons in, did they end up all paired? Yes, 2 and 2, all paired. We didn't have like a single electron anywhere. That's going to be the most important when we move forward. Okay, let's do an MO diagram of benzene. By the way, everybody seen the key to drawing MO diagrams in the handout? Right? That's exactly what we're doing. Benzene. We've got structure of benzene up there. First thing we want to do, how many p orbitals are we dealing with? Six. Benzene has 6 p orbitals. So let's draw the 6. We're going to do it right here. Doing benzene, yeah? 1, 2, 3, 4, 5, 6. So we've got 6 p orbitals. How many electrons in these p orbitals total for benzene? And if you're thinking right now, what in the world, what does that mean? Well, it's a simple structure. You should know structure, right? How many pi electrons in the system? 6 pi electrons. If you don't know that, you need to review structure. Okay, each p orbital has 1 electron, right? So we can take stock of what we're starting with. This is what we're starting with. Now let's do the MO diagram here. We're going to have this. We're going to have an energy midline. 6 p orbitals. How many MOs are we going to draw? 6 MOs, right? We had 10 p orbitals. How many would we draw? 10. So we're going to have 6 MOs. Now, we can draw them, put them in. In cyclobutadiene, we had 1, 2, 3, 4, right? The midline is always going to cut symmetrically through. In terms of energy. Not necessarily 2 and 2, but energy. How are these 6 going to be placed? When you go to a ring, you get degenerate orbitals. Instead of having 1, 1, 1, 1, we're actually going to end up with 2 that have the same energy. Those are called degenerate because of the cyclic nature. Let's see. I'm going to try to put this low and do them as we go up. Here's benzene. Everybody knows there's a p orbital on each one, right? How could these p orbitals interact? What's the best way they can interact? All in phase. How can we show that? Plus, 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 plus. That is, there's overlap all the way. Now that's overlap. Overlap all the way around, right? This is where they interact all constructively. And that's going to be your best molecular orbital. And that's going to sit down here at the lowest energy. Now, I'll draw another benzene ring. Instead of putting the p orbitals all the way around, I'm just going to put the signs, okay? P orbitals are there. What's the next best way? Or what's another way? You can't say they're going to interact all the way around. We've already done that. What's another way they can interact? When we showed the second one here, what did we use as our guide? Nodes. Number of nodes. How many nodes did the first one have? 0. How many does the next one have? 1. 0 nodes. There's no plane where you can cut through here and there's no electron density. There's electron density all through there. How many nodes is this level going to have? 1. So we can draw a node and then go from there. For example, we can cut right through here. A plane right through this. Now if I arbitrarily just say this is plus, what is this one going to be? Plus. And that one? Plus. What would this one be? Minus, because this tells us there's no overlap between here, so that's going to be plus and minus. What is this? Minus and minus. So that's where the orbitals combine with these 3 being in phase, these 3 being in phase, but there's no overlap between here. And that gives us a plane of no electron density. It's a node. And so this is going to have 1 node. What's the net bonding here? That's a bonding interaction. That's a bonding interaction. That's a bonding, 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 bonding. What's the net here? 6 bonding net. That's the best overlap you can get. What's the net bonding here? Bonding, 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 bonding. But what is this here? That's going to be called anti-bonding. And what is this? What's the net here? 2 bonding net. Because 2 anti-bondings cancel 2 bondings, you're left with 2 bonding net. So it's still a bonding molecular orbital, but it's not as good as the 6 bonding. When you have cyclic systems like these 2 we're doing now, you have possibility of degenerate orbitals. That is, we could get a node another way. The node could come right through here, actually through 2 carbons. And we can have a plane this way. You get 2 possibilities when you have a ring. Now if this was arbitrarily plus, what would this be? Plus. What would this be? Minus, because there's no overlap between them. Actually, it doesn't have to be minus because there's no overlap between them because there's a carbon between them. These carbons are not adjacent, so they're not going to be able to overlap anyway. But just to keep symmetry, I'm going to call that minus and this minus. So I see overlap here because it's constructive overlap leading to a bonding, and I see bonding here, but there's no bonding here, right? I mean, these are not even next to each other. What's the net here? There's no anti-bonding there. It's just, what's the net? Yeah, you see both of these are two bonding net. They have the same energy. So there's just two different ways to get it. We call those degenerate molecular orbitals. They have the same energy. Those two are here. Boom, boom. They're not as good as this one, but they're still bonding. They're still net bonding, and so they're below the midline. Now I kind of moved up. So there's three. How many more? We got to do three more, right? Let's start with the system here. How many nodes at this level? And we're going to have two nodes here. Now here we can get two nodes. Well, these, I'm going to do this one first. We can come right through here, but then we can also come through here. I think this is going to be it. I'll have to see the other one and make sure. Yeah, okay. If we just say that's plus, what is this going to be? Minus. What is this going to be? Just to keep our overall symmetry, I'm going to call that plus. And if that's plus, what's this? Minus. Here, there's no electron density on these two carbons, which you think about, kind of mind-boggling. This is all based on math. It's all based on mathematical combination of atomic orbitals. Higher level math gets you to this. We're using some symmetry of the molecule to help us here. What's this interaction here? Anti-bonding. What's this interaction? And that's all the interactions you have because these are not interacting because there's a carbon in between. What's the net here? Two anti-bonding net. This is an anti-bonding molecular orbital. Anti-bonding molecular orbitals are going to go above the energy midline. These are if they were isolated. If we start bonding, we go to lower energy. If we start anti-bonding, we're going to go to higher energy. There's actually another way to get this, though. We could get... Let me try to draw this very symmetrically. I think we're going to come through here and here. Two nodes. Let's see if that works. We should get two anti-bonding net. We're trying to draw degenerate. If this is plus, what is this? Plus, because there's no plane here. What is this? Negative, because see right through here, that means there's no electron density. That means these are not overlapping constructively. Now that's minus, what is this? Plus, plus, and that's minus. So what's the net? That's bonding, this is bonding, but what is this? Anti-bonding, what is this? What is that? Anti-bonding, and what is that? So what's the net? Two anti-bonding net. That's a different way to interact, but you get the same net result. So there's two there. Each of those has two nodes. The fact that 2 and 2 doesn't mean anything. That just happens. Okay, we got one more. The one more is going to go here. How many nodes is it going to have? How many nodes for this one? What's after 2? 3. So we can let the number of nodes be our guide. Nodes are always going to be symmetrical. Let's see how we can get 3. I'm going to move over here and do it. I've been doing the point. Let's see if I can figure out how to get 3. I think we're going to come. Here and here. So if that's plus, what is this? If that's minus, what is this? No, it's plus. See, there's no overlap here. That's what this plane means. What is this? What is this? Minus? What's the net here? Do you see it already? 6 anti-bonding net. Do you see that every one is anti-bonding? There's 6 of them. So that's worse than 2 anti-bonding, isn't it? It's higher in energy. It's up here. 3 nodes. That was our guide to help us get it. That's the highest energy. What we have on the board here is 6 different ways to combine these 6 orbitals. For example, they can all combine in phase, or actually here they all combine out of phase. And there's intermediate ways to combine. 6 different ways for them to combine. Now we have 6 molecular orbitals. See, this is a molecular orbital. It's kind of mind-boggling, but this is one orbital. It's just it's spread over the entire molecule, called a molecular orbital. But it can hold 2 electrons, and if you put 2 electrons in here, they're spread all over. If we put 2 electrons in this molecular orbital, you have electron density here and here, but there's none in the plane. Let's look at what these look like. Sort of another view. It's in the white handout. There you go. There are the 6 we just drew. Looking down from the top. So this has electron density all around. If you put 2 electrons in here, they're spread all the way around. See the plane? You have to think about what all this means with consequence, but basically now we have our MOs. Now we can put electrons in, just like you did in Gen Chem, off-call principle, Hund's rule, Pauli exclusion principle. How many electrons do we have to put in? 6. Where do you want to put the first one at? Right there? Where do you want to put the next one? You fill degenerates first. Well, there's no degenerate here, so the next one goes here, but opposite spin, Pauli exclusion principle. Where's the next one? 3. After this one, where does the next one go? 4. What's that? Filling degenerates first. What's that? Hund's rule? Is that Hund's rule? Where's the 5th one go? Now we can start pairing, and then we can pair there. There are your 6. What do you see? The most important thing that we will look for is, are they all paired? 2 pair, 2 electrons paired, 2 electrons paired. All electrons paired. What else is good? The electrons are in what type of orbitals? What type of molecular orbitals? What are these down below the midline called? Bonding. All electrons in bonding molecular orbitals. That's actually going to be secondary. The most important moving forward will be they're all paired. So in benzene, there's 2 electrons in this MO, there's 2 in this MO, and there's 2 in this MO. What does that really mean? We're not going to get much beyond this. If you want to know all that, it's really a mathematical foundation. MO is really an alternative to valence bonding. I mean, it's a different theory. In valence bonding, which we've always done, I mean, when we learned bonding to organic 1, it was valence bonding. In valence bonding, the atoms keep their orbitals. We just say they interact. Here we go to molecular orbitals. One thing this allows us is it allows us to see higher energy orbitals. And for example, when you do UV vis, you talk about electrons being excited. Well, this is what can happen. One of these electrons can be excited to this MO, a higher energy orbital. By the way, what is this level called? The one that has the highest energy molecular orbital. It's the highest occupied molecular orbital. What is this called? It's called the HOMO. Highest occupied molecular orbital. Now there's actually 2 there. Y'all heard of HOMOs? What's the other one? Not HOMO, but Peter? LUMO. LUMO. What does LUMO mean? Lowest unoccupied. Which is the lowest unoccupied? This level? Right? That's your LUMO level, right? Y'all did this in Gen Chem? No? So where have you heard HOMO and LUMO? Oh, this week? Y'all didn't hear HOMO and LUMO at Gen Chem? I'm trying to figure out what's taught in Gen Chem. Y'all didn't? Because when I took Gen Chem, we did HOMO and LUMO. No HOMO and LUMO? Okay. Well, that's HOMO and LUMO. It's just terminology, right? Any questions about benzene? Let's do cyclobutadiene and let's compare. Remember cyclobutadiene? Was it real stable? No. It's a cyclic conjugated system, but it's not stable. Well, the MO diagram will show us why. Y'all do ground state configurations in Gen Chem? Yeah. Let's do an MO diagram of cyclobutadiene. Down on the right. How many p orbitals are we dealing with? 4 p orbitals. How many electrons are we dealing with in this pi system? I mean, one electron overlap makes pi bond. One electron overlap makes pi bond. We can say there's overlap here. That's just the old-fashioned valence bonding, right? I mean, that's your 2 p orbitals, right? Each p orbital has 1 electron. Okay. This is usually just done to say we're going to work over here. Energy midline comes across here. How many MOs are we going to have to draw? 4. Let's see if we can draw them here, okay? What's the best way that they could overlap? All in phase. Plus, 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 plus. All in phase. And that's going to be down here. You're only going to have 1 at the bottom because there's only 1 way to be the best. Okay? What's this interaction? Bonding? What is that? What's this? Okay? So what is the net here? 4 bonding net. How many nodes? 0. Okay, let's try the next one. That's the first. We got to do 3 more. How many nodes on this one? It'll be 1 node. Let's just put it right there. Now, if this is plus, what is this? Plus. And what is this? And this? Yeah. See, there's overlap here, and that's bonding. There's overlap there, and that's bonding. So what do we have here? There's no electron density here because there's no overlap. No electron density, it's actually anti-bonding. And what is this? What's the net? 0. So it's neither bonding nor anti-bonding. What do you want to call it? Non-bonding. Called non-bonding. Now guess where non-bonding go on here? Do they go below, above, or on the midline? They actually go on the midline. Because they're non-bonding just like if they were not anything. So there's those 2. Oh, we hadn't did the other one. There's actually another one. Because we can also... How do you want to draw the node? This way? This way would actually be the same thing, just turn. I think it's going to come this way. Actually 2. And if this is plus, what do you want to make that? There's really no interaction here, but just for symmetry, mathematical symmetry, we're going to make it minus. What's the net here? Nothing. There's no bonding interactions. There's no anti-bonding interactions. These are the 2 here. All right, we got 1 more to draw. How many nodes is it going to have? I think we can do it like this. If this is plus, what is this? And what is this? There you go. This illustrates the overlap of these 4 in this manner. What's the overlap here? Anti-bonding, destructive overlap. Like 2 waves coming together and canceling everything out. How about here? Everything here is anti-bonding. What's the net here? 4 anti-bonding net. Where does it go? Below, on the midline, or above? 4 anti-bonding net. These are going to be called non-bonding. 0 node. This had 1 node, and this had 2. How many electrons do we have to put into these? I'm not going to show these. I don't think I have a picture of them. Okay. How many electrons do we have? Put 1 here. Where do you want to put the next one? Where's the next one? Where does the last one go? There you go. And if you look at an MO diagram of cyclobutadiene, what do you see? It's a diradical. What's a radical? Unpaired electron. There's an unpaired electron there, and there's an unpaired electron there. It's a diradical. That's why it's not stable. Not only is it a diradical, this is an electron in what type of orbital? What type of orbital is this? Yeah, it's a single electron on a non-bonding orbital. It's just set out there to... That's the big difference. Benzene, all the electrons are paired and they're in bonding molecular orbitals. Cyclobutadiene, it's a diradical. Does that make sense? Then you have to go back and say, okay, well, how did we get to all of this point? What does this look like? That's going to be the main thing. Remember, both benzene and cyclobutadiene are both cyclic conjugated systems. But one, all paired, this one not. Again, we're not really going to get into the foundation of molecular orbitals. If you want to learn more, you have to go do some reading about the math and how we get to that theory. I'm trying to show you enough to use it and to understand why one's stable and one's not. Sort of the terminology and the mechanics of building the MOs. It's also explained on that page that says, what? Key to drawing MO diagrams. Everything we did is right there. At the very bottom, there's a little trick. How you get the MO orbitals, the energy orbitals set up this here. The trick is for cyclic conjugated systems, if you draw the molecule with the point at the bottom, for example, cyclobutadiene, this is it with the point at the bottom. If you just make each atom an orbital, you get that setup. And the midline just comes straight through the molecule. 1, 2 on the line here. Now if you draw benzene with the point at the bottom, what do you get? 1, 2, 2, and if I pointed a little higher, it'd be higher. Midline comes right through. 1, 2, 2, 1, just like we did, yeah? That's described over there. That's called the Frost mnemonic, or the Polygon Method. All right? A lot of this is based on symmetry and also on mathematical considerations. Question? What we're next going to do is, we did a 4 and a 6, let's do an 8. Questions while I'm erasing? The 8 is shown, hopefully on the lab here. Yeah. Let's get Pokel's rule. Let's do an 8 here, and we're kind of looking at all this. Here's the 8. It's called cyclooctatetraene. Ring 8, 4 double bonds. Is that a cyclic conjugated system? Does it have p orbitals all the way around that are conjugated? Yeah, I mean each atom has a p orbital. If we want to take time to draw them, isn't that a p orbital there? And then don't we have p orbitals here? Right? That's overlapping, that's overlapping, that's overlapping, that's overlapping. But aren't these two overlapping? Sure they are. It's a cyclic conjugated system. Or is it not? We have to come back and modify this maybe. First question you want to ask is it a cyclic conjugated system? So what? Is it yes or no? How about yes or no? Are you saying that it doesn't have p orbitals all the way around that are lined up? That's the first question you want to ask. Is it yes or no? Sarah? Oh wait, y'all see Sarah on that poster over there in the JSAC? I won't go there. She's over there at the front door.
I would say yes.
Well, I mean, that's the question you need to ask. I can't answer it for you. I mean, that was discussed in Organic 1 the first couple of weeks. And then when you did resonance, everybody did resonance in Organic 1? Okay. So you should know how to answer. That's the first question you want to ask. For now, let's say yes. Okay. If it's a cyclically conjugated system, then we can do an MO like we've done. How many p orbitals are we dealing with here? 8 p orbitals. How many electrons in the system? One electron overlap, make pi bond. We do that all the way around. Each one has 8, right? 8 pi electrons. Again, it's no good for me to tell you this answer because what if we go to another system? Do I have to tell you that answer also? Those are the questions you got to ask yourself and make sure you know. Right there. That's the starting point. This point, I see we do need to look at Huckel's rule. Okay, we did a 6 and a 4. When we go to an 8, you don't actually have to reinvent and go through it all the time. Huckel's rule states that a cyclic conjugated pi system with 4n plus 2 electrons will be aromatic, where n is just an integer, a number, including 0. It could be 0, it could be 1, it could be 2, or 3, or 4, or whatever number you come up with. Now benzene had how many pi electrons? Cyclic conjugated system, yes. 6 pi electrons? What we want to ask is that a 4n plus 2 number? Alternatively, a cyclic conjugated pi system with 4n electrons will be anti-aromatic. Is this a 4n number or a 4n plus 2? Where n is what? Where n equals 1. It's a 4n plus 2 number. Huckel's rule says it will be aromatic. Now for cyclobutadiene, how many pi electrons were in that molecule? 4. Okay? 4 pi electrons. Is this a 4n plus 2 number? Well, if n was 0, what would this equal? 2. If n was 1, what would this equal? 6. If it was 2, what would this equal? So it's 2, 6, 10. What if it was 3? 14. See, these are going to be aromatic. 4n. What if n was 0? You can't have anything with 0, so that's not. What if it was 1? 4. What if it was 2? 8. What if it was 3? Well, 4, 8, 12, 16. Those are 4n numbers, where n is an integer. So is this a 4n plus 2 or 4n? That's a 4n number, where n equals what? 1. Huckel's rule tells us this will be anti-aromatic. What is it really telling us? If you do an MO diagram of any of these, you'll end up with all electrons paired. If you do an MO diagram with any of these, you'll end up with a diradical. Huckel recognized that and said, hey, everybody, look what I'm telling you. Anytime it's a 4n number, you're going to get a diradical. So he's kind of helping you out there. So, using that rule, what do we expect for this guy? Aromatic or anti-aromatic? Anti? Okay. So if it's anti, what type of behavior do you expect for this compound? Properties? Very unstable? Because you're saying it's a diradical. While we're considering properties, let's quickly do an MO for it. Eight with 1 electron each. Now I'm going to do this kind of quick instead of giving you the whole spill. Set it up. 8. Everybody trust me that there's going to be one at the bottom where they all interact the best way. From there you're going to go 2, 2, 2 until you run out. Before I do it over there, I'm going to do it here because I'm going to consider symmetry. I'm going to have 1 and I'm going to go 2, 2, 2 until I run out. How many do I have? 1 more. If you have 1 more, he's going to go at the top here. Now the midline cuts symmetrically through. How's it going to cut through? Now I should have just did it over there, but sometimes I like to look at it. Okay. Now seeing this, what type of MOs are these 3? Bonding. What are these 3? What are these 2 on the line? Okay. Let's put the electrons in. I should be over there. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8. What do I end up with? Diradical. That's not a surprise because Huckel's rule, that's basically what Huckel's rule told us. Huckel's rule was saying, hey guys, if you got 4 electrons, it's going to be a diradical. If N was 4, it'd be 16. Guarantee if you do a 16, you'll go diradical. Okay? So what type of properties do we expect for this? Very unstable? Well, guess what? That compound is very stable. That compound's not very unstable. I could bring this home and show it to you. I could heat it up. It wouldn't do anything. It doesn't have anti-aromatic properties. It's because it's not anti-aromatic. This compound is not anti-aromatic. Because it's not cyclically conjugated. And I should have brought my model. What does this assume? So if you got this wrong, this compound is actually not cyclic conjugated. And I should have brought the model. Let's bring a model. I brought a 6-member ring. We'll have to look at it next time. Let me ask you this. Do you think this compound wants to be anti-aromatic? Of course not. Nobody wants to be anti-aromatic. What happens is, if we had a model, if this is cyclically conjugated, that means it's completely planar. Okay? Pretend I got 8 fingers. It's a pi system here. Okay? Okay? There they is. They're all interacting, pi system, planar. But if it's planar, guess what? You become anti-aromatic and you get all this MOs and it's not good. So the molecule wants to avoid that. Would the molecule prefer to be in a better energy conformation? Sure. So what does it do? It adopts a non-planar conformation to avoid that. If I had a model, I'd show you. This is actually a tub-shaped molecule. Okay, I'll bring a model and we'll look at it next time. It's also in the book. Actually, there's actually very few anti-aromatic compounds. Because if they can avoid it, they do. They avoid it by becoming not cyclic conjugated adopted a non-planar, and game over. Now what you should certainly know is, would you call that compound aromatic? No. To be aromatic, how many pi electrons you got to have? 4n plus 2. Does that have 4n plus 2? No. It's certainly not aromatic. It's potentially anti, as long as it's cyclically conjugated. We'll see what type of questions come up. Let's move on. Huckel's rule is only if the system is cyclically conjugated and planar. If it's not, game over. It's not aromatic. This is nothing more than just a tetrahene, a compound with 4 pi bonds. It reacts with bromine to give addition, transaddition, just like any alkene. Okay, let's do a few others. How about this guy? Aromatic, anti-aromatic, or none? Is it cyclically conjugated? Does every atom have a p orbital in the ring? Question? Thank you for that question, because it's a great question. It may look like it's cyclically conjugated, but how do you know it actually is? Well, you'd have to do some modeling. But you also, the question you would ask is, well, first off, let's assume it is. If it is, let's just say yes for now, because it certainly looks like it. If it is it aromatic or anti? 2, 4, 6, 8, 10. 10 pi electrons. Is that a 4n number? No, there's no way to get 10 if you have 4n. N would have to be 2.5. N has to be a whole number. That's a 4n plus 2 number, where n is 2. Aromatic. If planar, cyclically conjugated. Now, do you think it wants to be cyclically conjugated or not? It doesn't want to be aromatic? No, aromatic is a good thing. If a compound can be aromatic, it wants to be. It's superstability. Do you think it wants to be planar? Yes. It wants to be. Is there anything to keep it from not being? Actually, in this case, there is not. I'll show you a case later. This compound is aromatic. How about this one over here? Is it a cyclically conjugated system? Does every atom in the ring have a p orbital, and are they adjacent? Can they potentially all be planar and line up? So over here we're going to say yes, same question. How many pi electrons? 2, 4, 6, 8, 10? It's actually kind of an isomer of that. This is all cis. So what's the answer? Aromatic, anti? It's either aromatic or nothing. It's not anti. This one is actually non-aromatic. But why? Because it's not actually cyclically conjugated. It may look like it. But if we draw in this H here, and we draw in that H, those two H's are in there and they're like this. By the way, how do we know it's non-aromatic? What type of evidence would you collect on it? How do aromatic compounds behave versus non-aromatic compounds? We talked about that, right? We talked about 4 or 5 different differences. What experiment could you do to see if it's non-aromatic versus aromatic? Heat it and see what?
See if it like makes
Well, non-aromatic compounds are not necessarily bad. I mean, if you heat up ethanol, it's non-aromatic. It doesn't do anything. We spent the majority of the first lecture on ways to determine aromaticity. Why do we do that? This is nothing more than theory. How would you prove or disprove it's non-aromatic? If I brought you a compound and said, here, is this compound aromatic or non-aromatic, what would you do? Somebody get an H&MR and look for what? Aromatic signals would be in what region? If it was non-aromatic and thus just an alkene all the way around, where would these signals be? 5 to 6? Okay. Well, guess what? If you do an NMR of this, the signals are like 5 to 6. They're not in the aromatic region. I mean, I know it's not aromatic. But why? I mean, it's got 10 pi electrons. The reason why is it's not actually cyclic conjugated. Because these H's right here interfere, what does it make the ring do? It makes it pucker, and the p orbitals do like this. They're no longer, just because they're next door, does that mean they're conjugated? No, they have to be like this. What if they're next door and they're like this? They're not conjugated. Okay? It's not. What about this? Naphthalene. This is where we remove the H's and make a pi bond here. Is that? Yes, it is. Naphthalene is aromatic because if we get rid of the H's and just make the carbons bond, you don't have the puckering. These two show signals at 7 to 8 in the NMR. This one has signals about 5 to 6. There's also other things that are different. We're out of time, you know? Please look ahead. We'll look at heteroaromatic systems, cations and anions. We'll pass these back as you're leaving. This is from the Wednesday lab. Please just pick it up down here. Vidya? Hama? Kay? Sean? Muggin? Sean Thomas?
Yeah.
Matt Albert? Sonny? Jason? Karen? Sarah? Precious? Cooper? Valerie? Camille? Sarah Ray? John? Ray? You get mad. Brianna? Brittany Bennett? Ariel? Adam? Stephanie Turner? Andy Bean? Drew? Asma?
K out of 3. I don't know what the hell it is.
Maybe the enzyme.
And we got on the subject of like classes and everything I was talking about. He said he's in high school, so I thought that was pretty cool.
They're representing a company or?
I think it was just like he's friends with one of the guys on the dugout for fundraising team. So
Yeah, man, it's just one of those things.
I was looking outside, it's warm in here.
still studying.
So you kind of became this little backyard redneck psychology.
Okay, so right. This is the judge-free zone.
Thank you.
All right.